was nice meeting you today. The cold day, so much cold, and the pollution, and you have to come by transport here. Lot of traffic, I can understand. Okay, so we will start slowly. So yesterday we were discussing about the basics of power quality and what are the issues, what is basically the power quality. We discussed all these things, and we said power quality is voltage quality. Then we discussed what is point of common coupling, and we gave these examples, and then we were talking about the survey results on the causes of power quality problems. The perception of clients is different than the perception of utility companies. Then the justification of interest in power quality, why the harmonics levels are increasing in power network, load equipment is more sensitive, this all things we discussed. Then the protection against power quality is basically the protection against interruption of production, which is very costly. Even if for few minutes in one day there is no electricity, so it is not just a matter of a few minutes. It costs only in the North America more than $100 billion every year. So this is what actually we can achieve if we have a better power quality residential customer. Then we discuss the different issues. What are the power quality impulsive transients, right? We saw this thing. And then impulsive over voltage and oscillatory transient, all these things we have discussed. Then voltage sag dip for few cycles, we have discussed this thing, and what problems voltage sag may cause, and the example of voltage sag if you have single line to ground fault, or if a large motor is starting, then it draws a lot of current, 5-6 times of the nominal current or rated current of the machine. So it will cause a huge drop in the impedance of the line and causing. Then swells temporary over voltages for few seconds. We have few cycles, right? So we discussed this thing, causes and what problems it may cause, and then example of temporary over voltage. Then short interruptions, this is what we were seeing, that for few minutes of cycles, if there is no electricity, so it costs a lot of money, right? And it causes the following problems, impact on industrial products and those things. Then we were talking about under voltage for more than 1 minute, so we may call it brownout also, and then over voltages. So everything we have discussed. Sustained interruptions for more than 1 minute, then we call it sustained interruptions, right? And then we were talking about voltage unbalance and how we are tackling this situation. And in transmission lines, we use transposition of conductors by shifting the position of the conductors. And then we were talking about waveform distortions. There are 5 types of waveform distortions: DC offset, harmonics, interharmonics, notching and noise. So this is DC offset. It may cause the saturation of transformer core, right? And then we were talking about the harmonics, how we can use the Fourier series. And today we will discuss briefly the Fourier series also. I know you have already studied in your undergraduation, but just to have a basic idea how to use the Fourier series and how to simplify the calculation, that we will study also today. Then different types of single phase diode bridge rectifiers, you see, square wave and what are the harmonics created, and if you have RC load, diode bridge rectifier with RC load, it causes lot of harmonics and lot of THD in the system. So we were talking, and then we were talking about what problems harmonics cause, okay, increase in losses in conductors, and the reason we saw like skin effect, ohmic losses, and then we were talking about the ferromagnetic losses like hysteresis losses, eddy current losses. So these are very important issues. If we have the harmonics, high frequency is there, so hysteresis losses are proportional to the frequency, while eddy current losses are proportional to the square of the frequency. So we will see perhaps again this little bit, and then degradation and considerable reduction of capacitor's life. Capacitor may attract higher harmonics because the reactive in capacitance it value decreases, and it may attract higher harmonics. Then voltage distortion, heating and torque pulsation in motors. Yeah, we discussed heating and pulsation of torque pulsation in motors, and we discussed how the fundamental frequency is generating rotating magnetic field in the air gap between stator and rotor, and a stable torque is produced and the rotor rotates in the same direction as rotating magnetic field. And then we have, suppose, voltage distortion at the terminal, then the fifth harmonic may be there, sixth, seventh harmonic currents may flow in the motor, then the fifth harmonic, as we will see today also, and why fifth harmonic is a negative sequence harmonic and seventh harmonic is a positive sequence harmonic, we will see that today. And so fifth harmonic will generate the torque in the opposite direction, and it will be having the frequency 5 times of the fundamental, although amplitude is 1/5, then but still it has some parasitic effect. And the seventh harmonic then is the positive sequence harmonic, so it will generate the torque in the same direction as fundamental frequency is generating, but the frequency is 7 times, so it will rotate with the 7 times faster than the fundamental frequency which generate the rotating magnetic field. So this is very important to know why there is a heating, and then heating is there because you are having harmonics, and fifth harmonic, 7th, 11th, 13th, 17th, 19th, those harmonics are there, and then they will generate extra losses in the core, in the rotor and stator material because of the ferromagnetic losses, hysteresis losses, and the eddy current losses. And then large neutral current, of course, we know that in normal balanced system, if we have IA, IB, IC, the sum we can say, okay, because of the Kirchhoff's current law, the sum will be 0, but because they are 120 degree apart, right, phase shifting. But if you have the zero sequence current, then they are in the same phase. So instead of cancelling each other, they will add up. So that's why the neutral current problem may be there. Then we're talking about the standard 519. Initially it was 1992, but it has been updated in 2014 and 2022, and they have little bit changed. So there are some minor changes, but for us they are not any major change. Then we were talking about interharmonics, same type of problem, and then we were talking about the notching, drop of voltage during commutation of current, because there is a source inductance which will prevent the current to reduce to 0 instantaneously, so it will take some time because of inductance, and in another set of thyristor it will take some time to build up the current, so there is a commutation overlap, and because of that we have the voltage drop. So all these things we have discussed. So you see voltage notching, and then we observe at point A here, and then we calculate the depth and the width of the notch, and then we can calculate the surface, and there are certain norms how much depth and surface you can have from notching for special applications, for general systems, and for dedicated systems. Those are different values. Then we were talking about noise, those things we have discussed. Then we were talking about flicker or voltage fluctuations. These are in comfort to the eye, although they may not affect the other apparatus phenomena, but they are in comfort in the eyes. So earlier we were thinking that the incandescent lamps are affected and perhaps LEDs may not affect, but I have come to know that LEDs are also affected sometime in certain cases because of the voltage fluctuations. And then the power frequency, as you can see, if you see the period from here for one cycle, this is the period, but here the period is less. So the power frequency variation, this is the power frequency variation. And you already know, because the frequency is basically the dynamic equilibrium between the load and power generated. So as you already know, in big power plants, suppose there's a hydropower plants and there's a speed governor and water is flowing, it is keeping, the speed governor is keeping the speed constant. So that's why you have the constant frequency 50 Hertz or 60 Hertz. But if there is a sudden change, big change on the load, and if load is increased too much, then it will generate the currents which are flowing in the stator winding, and large torque, electromagnetic torque is generated, which will be a braking effect on the rotation of the rotor. And then the meantime governor is taking effect, flowing more water, so that the speed is remain constant. So this is basically for it. This effect is not much seen for large generators, but there may be some cases, but the effect you see false zero crossing. So if variation in frequency is there, so your equipment may malfunction because it is false zero crossing, and it's the same type of thing which we have seen in voltage notching, that if there is a big notch crossing the zero, so it will be false zero crossing. Okay. So according to Hydro-Quebec statistics, Hydro-Quebec is a utility company in the province of Quebec. In the province of Quebec, we have around 44,000 megawatt of power generation in province of Quebec. And I will discuss that thing after 2-3 lectures, that this is very interesting, that in the Quebec 100% electricity is generated by non-polluting sources. Okay, 44,000 megawatt. Out of 44,000 megawatt, 40,000 megawatt is hydro electricity, and 4,000 megawatt is wind energy, and there is very less solar energy, but that I will discuss after 2-3 lectures. I will discuss the reason why it is so. So in the province of Quebec, 100% electricity is pollution free, clean energy. Okay, so Hydro-Quebec is the utility company for the province of Quebec, and according to Hydro-Quebec statistics, the average of fundamental frequency on network should be as follows. Main network 60 plus minus 0.6 Hertz, that is 1% variation. Okay, or between 59.4 Hertz to 60.6 Hertz during 99% of the time. So this is their standard. Isolated networks in remote areas, because there are so many remote areas, and I will discuss that also later on, why there are so many remote areas and why we cannot connect the grid to those remote areas, because they are thousands of kilometers away and it is not economical to put a transmission line there. So there are 200 communities living in the north of Canada which are not connected to the main grid. They are totally dependent 100% on diesel generators. So that is the topic. After 2-3 lectures I will be discussing about this thing. So in isolated networks in remote areas, 60 plus minus 4 Hz or between 56 Hz to 64 Hz. So this is what they expect, because it is a small power network, and in a small, if you have variation even small, so that counts. According to Indian Electricity Grid Code enforced by Central Electricity Regulatory Commission, okay, permissible frequency band on the national grid, this is because you have 50 Hz, so 49.9 Hz to 50.05 Hz. So this is the Indian Electricity Grid Code. For isolated network, it is not defined. Right now it is, because perhaps in India there are not many, because 2 years ago I heard that all areas connected with the main grid now, but I don't know in India. So maybe perhaps it is not that important, because there are not many isolated communities perhaps in India. But if they are there, so they are working accordingly. Okay. Power's frequency variation may be caused by a fault on high voltage transmission line, because if power frequency is changing, tripping of large load, loss of control of large power. So these may be the reason that power frequency variation may be there. Now if you see the different factors concerning the harmony, there are so many factors. So we need not to go to all those factors. I will just discuss the basic one. As you can see that THD, for our power quality course, total harmonic distortion, is very important, and you people already know this is the formula to calculate total harmonic distortion of voltage, and the same type of equation you get for the current. So here VH, you can see this is the RMS voltage of individual harmonic component, and V1, or you can say I1, V1 is basically RMS voltage of fundamental component. Yesterday one student was asking what is RMS value, but that is very reasonable question to ask. Some student was, perhaps Professor Madhusudan was also there. So please don't worry about this. This is very valid question. Actually, what you can say RMS, physically what you can say RMS value, if there is certain resistance and current is flowing, so RMS current will heat up, the resistance losses will be same as almost DC current is flowing. So that is why we call it effective current or RMS current. So physically you can say, otherwise V divided by √2, that is the mathematical equation, that is fine. But the losses caused in the resistance by RMS current, suppose 10 ampere RMS current is flowing through the resistance, it will cause the same losses as 10 ampere DC current is flowing. So physically approximately we can say certain like this, okay. So RMS voltage of V1, RMS voltage of fundamental component, and same thing for THD of current. So I1 is, this is the RMS current of fundamental component, and IH is the RMS current of individual harmonic component. So now you see harmonic here starting from second, H is equal to 1 is the fundamental frequency. So starting from second harmonic, and here it says infinity, but recently they have made changes in IEEE standard 519 in 2022 and 2014 that they are saying it is good enough to go until 50th harmonic. So we need not to say that infinity or above 50th harmonic. After 50th harmonic, that is good. Perhaps because standards are made by a group of academicians and engineers from the industry, so they know very well their work. So that's why perhaps there might be certain reason that they say, okay, harmonics above 50th harmonic may not have very important effect on the system. So perhaps they have limited it up to 50th harmonic. Okay. So this is just, I tell the student, okay, in 5 minutes calculate TSD of voltage if this is the, so you need not to calculate, but later on we will have. Another important thing is the TDD. So generally as power quality engineer, I have seen in most of the papers they don't mention TDD, right? They are concerned because THD is basically for a smaller system like our system, like not in megawatt or big system, but TDD is used, total demand distortion, used for large industrial systems. Okay, assessing long-term performance as it relates to the system's full load capacity. THD is used for smaller, less complex system. So our system, what we work in our labs for small system, the THD is good enough. But if you are talking about large big system, like 2 years ago, one of my student was doing internship in a company in the north of Quebec. Rio Tinto is a big Australian company. They do aluminium products. They have a very big plant in the north of Quebec. Now there may be a problem there because of the tariffs posed by President Trump. So they were saying, okay, 50% tariff on the iron products which are coming from Canada to US, and 25% and 25% aluminium. And then because he was not satisfied, President Trump, so he said, okay, now we will have 50% tariff. So everybody was very scared, especially those companies who are working in the, even I think this Mittals, they were having one iron ore plant there. So for many years they are there. Nobody thought about this thing that Canada is totally dependent on US to supply this steel and aluminium. So now I don't know, they have not yet resolved the problem. So in Rio Tinto, so they have big transformers in multi-megawatt range transformers and system for processing aluminium. Okay, so there they have a lot of parallel product lines, and big transformers are connected in parallel. So there we should be worried about the phase shifting, which we will be discussing soon. Phase shifting between the transformer. And this is what I was telling earlier yesterday in my speech, that one engineer suggests the management, okay, we can have similar type of system for second line of production. That we will come later. But talking about TDD, this is for large industrial plants, and you can see this is the same as we have in THD, starting from second harmonic, and but here you see this is the RMS value of maximum fundamental load current. calculated as the average of maximum monthly demand currents for 12 months. So this is how, instead of putting I1 here, which is RMS current of fundamental component, so here it is more complicated to calculate IL, and in some cases data may also not be available, so it's not that easy to calculate TDD. For our system TSD is good enough, but TDD also has the same limits. Okay, so I will come to that later. So TD also has the same limit, like we always talk 5%, like a TSD maximum, but individual harmonic current limit may be different. So this we will see the table, what is that table. So this is the difference between TSD and TDD. Now the mathematical part of the RMS current we were talking about, we were saying okay, RMS current may have effectively same losses in the resistance at the DC current. But if you see, this is how we calculate the effective RMS current. So starting from harmonic 1, there is some echoing effect. Okay. So here you can say first fundamental component of voltage you can take out, then starting from the second harmonic. Okay, so this is basically equal to this. It is basically the TSD formula, right? If you take it here and take the square of this, so this is what we have put, this equal to this. Okay, so you can simplify, and finally you can see that this is the relation between the effective RMS value of voltage and TSD of voltage. Same type of equations you can derive for RMS currents also, relation between TSD of current and RMS of current. Now DIN distortion index, generally in North American paper you don't see distortion all the time. We talk about TSD, but many companies and researchers in Europe, they use DIN instead of TSD, and there is a relation you can see here. It is same as TSD, but here instead of having V1 which is the RMS value of fundamental component of the voltage, we have this series. Okay, so you can take the square of this and you can simplify. You can take V1 out here. Okay, because I hear a echo is there, right? Okay. So here you can simplify it by this, this by this, and finally this is the relation between the DIN and the TSD. Okay. Because I hear the echo, but it is fine, it's okay. Sometime it comes the echo, perhaps. You also hear the echo? It's okay, it's okay. We'll manage, don't worry. Okay, so if you see the relation between the DIN and TSD, this is the relation. So DIN is here and TSD is here, and if you draw the curve for initial some value of TSD, the relationship is linear between the DIN and TSD. And when the TSD value increases, pardon? No, they are using, but some researchers still, this is one factor which may have, otherwise it is basically the same thing. You can represent a DIN or TSD, but it is just that the maximum value of DIN is 1. Yeah, if TSD goes very high, you can say DIN is 1. DIN 1 means TSD is very high. Okay, so it's okay. Now see this table, harmonic voltage distortion limits in percent of nominal fundamental frequency for, this is new, harmonics less than 50th harmonic. Okay, and they also have added, earlier this was not there in IEEE standard 519 1992, this was not there, but I think they have recently added this thing. Otherwise this was there, that bus voltage at PCC is less than or equal to 69 kV. Individual harmonic voltage distortion limit is 3%, and THD total should be less than 5%. We already know this thing, right? You are already using it in the lab. And if the voltage is between 69 kV and 161 kV, higher voltage, so this limit is reduced 1.5%, and THD limit is reduced to 2.5%. And if this is very high voltage, more than 161 kV, then individual harmonic voltage distortion limit is 1%. So as the higher voltage is becoming higher and higher, we have a more severe limitation on individual harmonics, as well as THD also 1.5%, because they don't expect you to have more harmonics on the transmission high voltage side. Okay, and then this is, so less than 1 kV, you already know in your lab. So you see 8%. I was surprised to see this. So for a smaller system, it is 8%, not 5% basically if you are having less than 1 kV. This is the new I saw in perhaps the new modification. So just check it, okay. Now odd harmonic current distortion limit in percent, here TDD is written, but the same limits are for THD also. Okay, so if the size of the system, distribution system increases, because this is the short circuit current divided by the load current. So if short circuit level is increasing, it means perhaps the circuit breaker capacity, perhaps they might be putting more, so that that large system may have large current. So that's why you see, starting from less than 20 ratio, it may be more than 1000 here. And this is how the limits are changing here. If harmonic is less than 11th harmonic, like 3rd harmonic, 5th, 7th, up to 11th harmonic, this is 4% for individual harmonic, okay. And then we have, if size of the system is increased, we can go to 7%, for larger size 10%, and if the size is more, then we can go to 15% individual harmonic, while total you see is still for a smaller system 5%, and then larger system this limit is increasing. As far as higher harmonics are concerned, if harmonics are between 11th and 17th harmonic, like 11th, 13th or 15th, those harmonics, limit is to see, this is reduced. So if harmonic ranking is increasing, so limit is also more severe. For higher frequency harmonics, limit is more severe. You see here it's 2, then from 17th to 23 it is 1.5, from 23 to 35 it is 0.6, and harmonics ranking more than 35 up to, now we can say up to 50th harmonic, okay, this is 0.3%. Okay, so this is how you can interpret it, that as the system size, distribution size increasing, you can tolerate higher level of harmonics. But as the harmonic ranking is increasing, you have to have more severe limitations on the limit of harmonic, as well as you can see the THD, this thing. This was for voltage less than or equal to 69 kV. But if voltage level is between 69 kV and 161 kV, then you see it is half of these. So if the system is 20 short circuit current divided by load current is 20, then instead of 4 you have 2 here, instead of 7 you have 3.5 here, instead of 10 you have 5 here, so half of these here, 15, 7.5. Same thing for other ranges also. See, this is half, instead of 2 you have 1, 3.5, so 7 is 3.5. okay. Same thing here, you see, almost going half of all those values. So if the voltage level is increasing, you have to have a more severe limitations on harmonic, and here you can see also half THD total 8, instead of 8 you have 4, instead of 12 you have 6, instead of 15 7.5, instead of 20 you have 10. For the voltage more than 161 kV, these are almost same. Here there is an error, this is 20 here. So, and see, these are almost same, not much change here. So this is IEEE standard 519, recently updated, but these are odd harmonic limits. But if you are having a even harmonics, it will have more severe effect on the system. Even harmonics are not desired, not at all. So they have 25% limit. So whatever values you are having, calculate the 25% limit of that, and that is for even harmonics. Then we can talk about the K factor. So K factor, this is the formula for K factor. Here IH, RMS value of harmonic H, this thing, right? HM harmonic you can say. And starting from 1 to, I think this should, instead of infinity, we can put here 50th harmonic. Okay. I effective RMS, effective value of load nominal current. So what is basically factor K? It represents transformer's ability to handle harmonic currents, and they have standardized values. So engineers in the industry, because you cannot have infinite number of different transformers, so they have put, okay, K factor value may be 4, 9, 13, 20, 30, 40, up to 50. Okay, K factor of 1 is for linear load. So you have a simple transformer, balanced system, linear load, so you don't have to worry about harmonics. So you can have K equal to 1, which we generally do even in transmission and there. While factor K of 50 is of severe harmonic distortions. So if you think then that there is a load is such kind which is generating lot of harmonics, and those harmonics will flow through transformer windings, higher frequency harmonics, so it will have lot of losses, ferromagnetic losses. See, ferromagnetic losses, hysteresis loss and eddy current loss, right? You know the hysteresis loss. What is hysteresis loss? Hysteresis loss is something like this, right? Flux density, relationship between flux density and magnetic field intensity H. So area within this loop, it represents the losses. So we call this the hysteresis losses. So those hysteresis losses are proportional to the frequency. So if you have the fifth harmonic, suppose you have fundamental frequency. So fundamental frequency, this is fine, you have certain hysteresis losses, eddy current losses. But if you have a fifth harmonic, then hysteresis losses will be maybe 5 times of hysteresis losses of the fundamental frequency. And seventh harmonic, no, fifth harmonic, if you are having fifth harmonic and you see the eddy current losses are proportional to the square of the frequency. So it means whatever eddy current losses you are having with the fundamental frequency, whatever eddy current losses you are having, you will have 25 times more eddy current losses if you have a fifth harmonic. And if you have a seventh harmonic, then the eddy current losses will be 49 times more, which you are having eddy current losses at fundamental frequency. So this is a very serious thing. So if you are having higher harmonics, they may have a lot of heating. So this is heating up the core, and the temperature of the motor or transformer will increase more. And you cannot have more temperature, perhaps some relay will trip because higher temperature is there, because you have to protect your transformer or motor, you have to protect it from heating up. Otherwise, the insulation may burn down and it may reduce the life of your transformer. So you have to basically derate it, transformer. Sometimes you may not go more than 50% of the nominal load. So this is the importance of K factor here. Now there are different other factors, okay, like different factors concerning the sustained interruptions, outages. Outages means you have long-term outages. When we say outages, it may be in hours, perhaps, you don't know. Okay, so some indexes. One is SCI-Fi. This index is basically used by managers to manage the system basically. So not as an engineer you will be using, but if you are a manager of certain utility or certain area, so you should be concerned about this thing. So SCI-Fi is System Average Interruption Frequency Index. And what is SCI-Fi? Total number of interruptions per year of clients divided by total number of clients on the network. So suppose we say that there were 30 outages in 1 year, and total number, suppose there were 20 clients on that network. So what will be SCI-Fi? 1.5. So this is the SCI-Fi. And what is SCI-Fi? Customer Average Interruption Frequency Index. This is system average. Here it is customer average. So total number of interruptions per year of the clients divided by total number of clients affected at least once. Here you don't care. In SCI-Fi you don't care if the certain clients are affected, but here clients affected at least once. So suppose 30 outages were there and only 5 clients were affected. So SCI-Fi will be 6. So if we say SCI-Fi equal to SCI-Fi, it means all the customers were affected the same way. But if we say SCI-Fi is much more than SCI-Fi, like here 6, it means certain customers were affected more than other customers. Maybe perhaps there is some small community and it is affected in comparison to other communities nearby. So manager has to see, okay, perhaps proper maintenance of local transformer was not done, or there may be some recurring problem, or some trees are there near the transmission line. Every year, 2 times every year in my locality, we have a hydro-quebec utility. So they come and check that the trees are not leaning on transmission line. So they cut down those trees so that if some wind is there, a storm, it may fall on the transmission line and it may affect the customers. So this is their work. They make it clear that there is no large tree near the distribution line. Then we have SID, System Average Interruption Duration Index. Duration. See, here we have the frequency, how many times, but SID is about the duration, for how long time. Okay, so SID, sum total of duration of interruptions per year of all the clients divided by total number of clients on the network. And KID, customer average interruption duration fixed. So see, this is almost the same. This is the same as here. Total number of duration, sum total of duration of interruptions per year of the clients. Maybe for 1 hour, 2 hours, for 10 hours, there was no electricity. But here, total number of clients. Here, total number of clients affected at least once. As the same kind of difference in SIFI and KIFI we saw, here it is. So basically, if we talk about SID and KID, it is about the duration, how long the system was down. It means technician was there on the site to see the problem and he was trying to correct, suppose for example, the transformer. So perhaps technician took long time to repair the transformer. So if the technician is taking long time, it means he has not been properly trained. So he should be trained for the maintenance work, right? So this is the duration and the frequency is different. So this is the difference between SID, KID and SIB, KIFI. There's a numerical question, but we don't have time for, but yeah, no, they cannot be equal because you see, total number of clients affected at least once. Pardon? Yeah. Yeah. Yeah.
Not once, maybe so many times.
Yeah. But sometimes what happens? So in Canada, sometimes what happens, we have our colony here and then there is a road and the other side there is another colony is there. Sometimes we don't have light but the electricity, but the other side of the road people have the electricity. So we are very jealous why he is getting the electricity, we don't have the electricity, because you can see. So sometimes it may happen because they may have different distribution transformer, our locality has different distribution transformer. So it may happen. Okay, so no, I will not go through this. Yeah. Who is waiting? Tea. Oh, tea is very important. We should have tea. Okay, good. Okay, good. And we apply it to the periodic function. And what is periodic function? Okay, which satisfies this condition. That is called the periodic function. Okay, so you can see ft0 is equal to ft0 minus t, ft0 plus t. So as an example, you can see at t0, this is the value, t plus t, this is value, this value. So you see, So this is how you represent a periodic waveform. And these are some of the examples of periodic function: full wave rectification, half wave rectification, and cathode ray CROs, sweeping generator. These are all example of Fourier series: square wave, triangular wave, rectangular wave, right? So these are all periodic function. So Fourier series is represented by, so any periodic function wave you can represent by this Fourier series. Okay, here AV, AN, BN, these are the Fourier coefficients. Okay, W0 is the fundamental frequency. So if you are talking about an integer, so you may have second harmonic, third harmonic, fourth. So these are the harmonic frequencies. Okay, so this is the Fourier series, and you can represent any periodic function using cosine and sine terms. So this is really amazing. Any periodic function can be represented by Fourier series. So how to calculate AV, average value, AK, the coefficient which is related with the cosinus. See, AN is related with the cosinus, BN is related with the sinus. So how to calculate BK for the kth element, right? This is how you can write the equations, how to calculate AK, BK and AB. Now I don't want to, suppose you have this periodic voltage and you have to represent the Fourier series. So first you have to calculate the Vt, this is Vm divided by T multiplied by with time, it is varying. So it is very simple to calculate this Vt. And the average value you can calculate. So these are the formula which we have seen here. You can apply and you can calculate the Fourier series of this periodic voltage. So this is how you see you have some average value is there, right? See, average, as if you can see, right? So this may be come here. So if you take the average, so perhaps Vm by 2, right? So physically also you can see this is Vm by 2. Then AK is equal to 0, BK you can calculate using that equation, this value. So finally, Fourier series for that wave you can write this way. You have the fundamental, you have second, third, all types of harmonics are there. So this is fundamental, and here multiplied by 2, second harmonic, third harmonic, like this. Now, sometime what happens, the engineers in the industry, they don't have much time, so to write equation AV, AK, BK and do the calculation. So basically we have to have some easier way to do this. So how you can simplify the task of analyzing and calculating. So there are certain symmetries you have to see. There is a even function symmetry, odd function symmetry, half wave symmetry and quarter wave symmetry. These are the symmetry. If you can find some symmetry in a periodic function wave, so then it will make your task very easy. You may take 1/4 of the time which you were taking otherwise, calculate AV, BK, AK, all those things. So what is even function symmetry? If the function is defined this way, ft is equal to f minus t, right? Like for example, ft is here f minus t is here. See, both are equal. This value equal to this. This value is equal to this. So this is how you can say that it is an even function. Ft is equal to f minus t. So if you can see the even function, then bk will be 0 for all k. See, you need not to calculate bk, otherwise you will calculate bk, okay, and finally you will find that it is 0. So you don't have to calculate bk. So you just calculate the average function and ak, which is related with the cosinus. So this makes analysis much simpler. Then if even symmetry is not there, you should check for odd function symmetry. Odd function symmetry is this function ft is equal to minus f minus t. For example, here, suppose this is ft, this is in the negative direction, so minus f minus t because of in the negative side, and here it is negative side. So this is the function. You can say this is an odd function if you can satisfy this thing. So if you see the periodic wave is odd symmetry, odd function symmetry, then you see you don't have to calculate AV. AK also, you don't have to calculate AK also. The only thing you have to calculate BK. So you see, this is how you can simplify the calculation. Just by looking at the wave shape, you can do the calculation fast. Then there is a half wave symmetry. Half wave symmetry, that you shift this wave shape by half cycle and take the inverse of this, then it should give the original thing, right? So this is what you can say. Now you will see, okay, I have a triangular wave, this, so what should I do now? It is not odd or even, so you can shift this axis and you can either have this way, right? So this is what you can say, that you can see here, this is equal to this is equal to this, or you can have, you could have shifted this wave shape here, this x here, so it will give this way, this. So what is basically, this is what, this is the odd function symmetry, right? We have already seen that f. So what you should do here, suppose this is the even function symmetry. This one is even function, right? Because t is equal to f minus t. So to verify if it is the half wave symmetry, you should shift by t by 2. So t by 2 is here. Okay. So instead of this wave, you have this wave. Take the inverse of this. So it is same as the original, right? So it means it has a half wave symmetry. You shifted it by half cycle, you shifted it by half cycle, took the inverse of this, and it is giving the original function. So this is half wave symmetry. Now you can have, as we have seen here, even function, or you can have odd function. Even function half wave symmetry, or odd function half wave symmetry, right? So if you have even function half wave symmetry, then for even function we have seen bk is equal to 0, av is equal to 0, ak is equal to 0 for k even, right? And so you have to calculate only ak. Okay. If function is odd, then ak will also be 0. For even function bk is 0, so you have to calculate only this. If the function is odd, then for all values of ak is 0, so you have to calculate only bk. See? So this is how you have simplified. You don't have to calculate AV, you don't have to calculate all these things. only one thing you have to calculate. If you can say this is half wave symmetry. Okay, now we have the quarter wave symmetry. Quarter wave symmetry is a half wave symmetry and in addition symmetry about the midpoint of positive or negative half cycle. Okay, so see, does it has half wave symmetry? Half wave symmetry means you shift it by t by 2 and take, so this is the wave shape, take the inverse of this, right? So basically this is same as the original. So it has the half wave symmetry. Does it have quarter wave symmetry? Quarter wave symmetry means you take this half cycle, draw a line in the middle at quarter wave and see both sides are symmetrical or not. So if they are symmetrical, you say, okay, this has half wave symmetry as well as it has the quarter wave symmetry. For example, if we see this, does it has half wave symmetry? This is half. This is the value, take the inverse of this. So it comes out as the original. So it has the half wave symmetry. But does it have quarter wave symmetry? You say see in the middle, there is no symmetry, there is no quarter wave symmetry. So though it is half wave symmetry, it does not have quarter wave symmetry. This is half wave symmetry as well as quarter wave symmetry. So if the function is made even and it has the quarter wave symmetry, then you have to calculate ak only for k odd. You don't have to calculate other things. Okay. Same way, if the quarter wave function is made odd, then you have to calculate only bk, this value for k odd. See, this is how you can simplify, you can save your time by not calculating the functions which you know those coefficient might be 0, right? So you don't have to calculate AB, AK and BK for K even, you have to calculate BK only for the K odds. Okay, now this, is it odd function or even function? This is odd, right? Because ft is equal to minus f minus t, right? This is coming here. So this is odd function. Does it has the half wave symmetry? This is t by 2. So shift by for half, shift it by 3. So this is the wave shape. Take inverse of this. So it means it has the half wave symmetry also. Does it have quarter wave symmetry? This is half cycle, middle of the half cycle. It has the quarter wave symmetry also, right? So what you have to calculate now? You don't have to calculate AV. You don't have to calculate AK, because see what you can see. Okay, if I draw a sinusoidal wave here, right? So it means it is related with BK, because AK is related with the cosinus term, right? So you don't have to calculate AV, you don't have to calculate AK for all values of K, you don't have to calculate BK for even values. Only thing you have to calculate this equation for K odd. Okay, so you can calculate the function IT, just see here, this IM divided with, this is T by 4. So you are calculating only for this portion. Okay, so it's not that difficult. You can calculate this and then finally you can calculate BK for this and K is odd. We don't have much time, so I don't want you to go through the numerical exercise. See, this is IT, and finally, this is the periodic Fourier series of this wave shape. So you have third harmonic, fifth harmonic, seventh, all odd harmonics are there. Right? Now I will like to discuss hurriedly the symmetrical component. Okay. Symmetrical component theory for unbalanced non-sinusoidal systems. Okay, because you have studied symmetrical component for unbalanced system, but not for non-sinusoidal. In your undergraduation, you have studied symmetrical component theory, which was good for unbalanced system, but not for the distorted system. So as you know, symmetrical components, these are the equations you can have. So if you have a three-phase unbalanced system, if you have a three-phase unbalanced system, it's difficult to analyze. Therefore, we use symmetrical components, and symmetrical components, you have positive sequence, you have negative sequence, and the zero sequence. So all the VA, VB, VC, they are unbalanced, so you have to use. Now what is positive sequence, what is negative sequence? See, yesterday night I draw the figure so that I don't waste my time here drawing it again. So see, these are windings 120 apart. Okay, winding A, winding B, and winding C. Then you have some magnet here, North Pole and South Pole. When you turn this magnet in this direction, so first it will induce in winding A, then winding B, and then winding C, right? So you have ABC, ABC, that sequence. That is called the positive sequence. You can represent it in this way also. There are three vectors, A, B, and C, and your eye is here, observator is here, and it is turning anti-clockwise. So you will have A, after this B will come here, after that C will come. So this cycle is there, ABC, ABC, ABC. That is positive sequence. Instead of turning the magnet